Okay. So now back to 6.1. Let's look at functions of several variables. Okay. So here's a function that we used to look at and study and work with. But this function has one variable, x, one independent variable, x. But here's a function of x and y, like x squared y plus 3y squared plus 4x plus 10y cubed. As you see, this function has two variables, x and y. Now, the first thing I would like to do is determine domain. So I'd like to look at a couple of functions. For example, here's a function number 11 on page 557. So here I have the square root of y minus 3x. And the question here is find domain. Well, I hope you remember that for this function, we have to write that x plus 1 is greater than or equal to 0, because this quantity has to be positive or 0. Then we move 1 to the other side, and we got the domain. What is the domain? -1 to infinity. Here's a different story. However, the condition doesn't change. I still have to write that y minus 3x is greater than or equal to 0. I can move 3x to the other side. Oops. And how do I write the domain? Well, I have two variables. Here's how we write the domain for such a function. This bar indicates having the property or such as. Here I have to write an ordered pair, x comma y. So the domain of such a function consists of ordered pairs having the property or such as y, any y coordinate is greater than or equal to 3 times the x coordinate. And this is the way we write the domain for such a function. So this function has two variables, f of x comma y. And this is the function, is the square root of y minus 3x. The domain of this function has to fulfill the same rules as before. Y minus 3x has to be greater than or equal to 0. Move 3x, I get this inequality. I can't solve it. It has two variables. All I have to do is now present the domain of such a function of two variables s with braces, not intervals. Braces. There are ways in which we can provide, depending on the function though. So it's the ordered pair, x comma y, such that, or such as, or having the property. What property? That any y coordinate has to be a number greater than or equal to 3 times the x coordinate. That's what this says. Otherwise, the function does not exist. Here is another domain. Allow me to make one up this time. So let's say I have a function of two variables, 1 over x squared minus 1 plus 1 over y. Well, I know that y cannot be
Zero.
Perfect. 0. And here I know that x cannot be
1.
Or if it's quadratic, I have to have two solutions.
-1.
Yes. And how do I write this domain? No problem. The domain is made out of ordered pairs having the property. They can be anything, but x can never be plus or minus, and minus plus or minus 1, and y cannot be 0. This is the domain of such a function. Okay, one more. Let's say I have f of x comma y is 1 over x plus y. What is the only condition here? That x plus y
cannot equal 0.
That's it. So the domain of this function consists of ordered pairs having the property whatever, but x plus y can never be 0. You can write it as x does not equal negative y. It's up to you. It's the same thing. Okay, so now let's look at number 5. We're given a function of two variables, and it's 2 to the x minus 3 to the y, and they're asking us to find f of 0 comma 2, f of 3 comma 1, and f of 2 comma 3. What does this mean? What are we asked to find?
Wouldn't you just plug in the points?
Absolutely. 0 here is 1, minus 2 here, 3 squared is 9, negative 8. 3 here is 8, minus 3 to the first power is 5. 2 here is 4, minus 3 to the third is 27, negative 23. That's it. So we know how to find domain of functions of several variables. We know how to evaluate functions of several variables. Let's look at a word problem. Let's say body surface area, 21. They're given us S of h comma w equals the square root of hw over 60. Let's see what this means. It's called a Most-Celler formula for approximating the surface area. Surface area. Okay? In square meters of a human, of any person, where h is the person's height in centimeters, and w is the weight, and it is in kilograms. Fine, use the formula to approximate the surface area of a person whose height is 165 centimeters and whose weight is 80 kilograms. One application of this, and you can say, who cares? One application of this is, that I know of, is for children and in general when they estimate the dosage for chemotherapy. So when somebody goes through chemo, they need to determine the surface area of the body in order to identify the dosage. I'm not sure how that works. I don't know the details. Okay, so all I have to do is replace h by 165, replace w by 80, calculate, and that will be the surface area in square meters. That's it. So s of 165 comma 80 will be the square root of 165 times 80 divided by 60. And this has to be in square meters. Okay, so I'll share, I'll go to the square root. You know me, I love my parentheses. 160, yes, most of the calculators these days do not require parentheses, but I don't know what type of calculator you have. And then outside completely divide by 60. And this is 1.9149, approximately 1.9149 square meters. Very useful formula for determining the surface area. Okay. That is it for section 6.1. So I do have, again, only my phone tells me the correct time. Yes, I have 8 minutes, 7 minutes. Okay. So let's start by, we're not going to finish 6.2. And the last section that will be finished next time will be 6.3. So what I would like you to do for Monday is 6.1 and 6.4. So we can ask, so we can answer questions, and 6.2 and 6.3 will be finished on Monday. Okay. Well, we're going to talk about derivatives of functions of several variables. Okay, well, those are not really derivatives. They are called partial, to be exact. So when we talk about a function with one variable, we say it's a derivative of that function. But when we talk about functions of several variables, we can only look at what it's called partial derivatives. What does that mean? And what is the notation? So I'm going to stop after I just mentioned one. So, okay, here's a function. Oops, sorry, I saw that. Here's a function of two variables. Let's say 2x squared y plus xy to the third. It's a function of two variables, x and y, and this is basically function variable z. Z is the function, x and y are the independent variables. If I want to find a derivative for such a function, I have to find the partial. What does that mean? And what is the notation? Here is the notation. It's not the straight df over dx. No, this is for functions of one variable. For functions of multiple variables, the notation for partial derivatives is this d, not this d. Okay? So partial derivative of f with respect to x. What does this mean? It means that the other variable, y, is considered fixed or a constant. It's considered a constant. This is also has the notation fx. So fx is the partial derivative of f with respect to x when y is a constant. I promise to stop right after I differentiate with respect to x. Okay. So fx or df over dx, but this d and d because it has more than one variable. Okay, so I differentiate with respect to x, and y is considered a constant. 2x times 2, 4xy. plus x and y is considered a constant. When I differentiate x, I get 1. So the constant stays. Now what if, and this is the last line, I promise, fy df over dy, which means x is fixed now. X is fixed. When I differentiate y, I get 1. So then it's 2x squared. Plus, I differentiate y cubed, 3x y squared. We're going to look at the second derivatives, partial derivatives, and mixture. But that's all I wanted to say. If you'd like to, just this page, the last page, if you'd like to